Good afternoon, everyone. I welcome every one of us to another question, another Math 101 assignment solution. And this question is from a quadratic root, and we are to prove that p raised to the power 3 minus q into brackets 3p plus 1 minus q squared is equals to 0. So let's dive into the steps in the solution to the question. So let's start with a quadratic equation. Now the root of a quadratic equation are simply the solution of the quadratic equation. That's the roots. So in this case, we say that let alpha and beta be equals to the root of the quadratic equation. And since the question is stating that the one of the roots is square of the other root, so it simply means that let's say that alpha is equals to beta squared. Since it was already stated in the question that one of the roots is equals to the square of the other root, so we say that alpha being one of the roots is equals to beta squared, that's the square of the other root. Right now, recall from basic relationship, that the sum of two roots alpha plus beta equals to minus b over a, and the product of two roots alpha beta is equals to c over a. And you know that for a general quadratic equation we have ax squared plus bx plus c. So by comparison, we have to compare the given question. So we compare the given question to the general form of a quadratic equation, ax squared plus bx plus c, where a is equals 1, b equals minus p, and c is equals to q. So from alpha plus beta equals minus b over a, alpha plus beta becomes minus p over 1. Similarly, alpha beta is equals to c over a. This implies that alpha beta is equals to q. Are you getting it? Now, it was already stated in the question that one of the roots is the square of the other. So this implies that alpha is equals to beta squared, since one of the roots is equals to beta squared. Similarly, alpha plus alpha squared is equals to minus p, because we already stated that alpha is equals to beta squared. So anywhere you are seeing alpha now, you are representing it with what? With beta squared. So let's move to the second case. This is what I was trying to explain in the last VN. So you can see clearly that we have alpha plus beta, that's p, and alpha beta q. When you substitute alpha equals to beta squared into the equation, we have alpha squared plus beta squared plus beta is equals to p, and beta cube is equals to q. So these are the two things that we will use in proving the equation. Beta squared plus beta equals to p, and beta cube is equals to q. Now, knowing fully well that alpha plus alpha squared is equals to minus p, and alpha cube is equals to q. Now, for the first equation, we want to take the cube root of both sides. Now, taking the cube root of both sides, we have this expansion. We expanded everything to be alpha raised to power 3 plus 3 alpha 4 plus 3 alpha 5 plus alpha raised to power of 6. Now, initially, we already know that alpha raised to power 3 is equals to q. If alpha raised to power 3 is equals to q, this implies that alpha raised to power 6 will be q raised to power 2. And alpha raised to power 5 will be alpha squared times alpha raised to power 3, and which is minus p times q. Similarly, alpha raised to power 4 can be written as alpha times alpha cube, which is alpha cube. So knowing all of these facts, we are going to substitute them back into the expansion that we have to get the proving that we want to prove. So by substituting all of the parameters that we have earlier, you notice that alpha raised to power 3 is q, and alpha raised to power 4 is alpha q, alpha raised to power 5 is pq, alpha raised to power 6 is q squared. So we made p raised to power 3 the subject of a formula, and we arrive at the final solution. So for those of us that have been watching the our videos so far and you've not subscribed, please take this moment to click the subscription button, also to like and make necessary comment. Thank you.